Hello, hello, hello. Um, hello, hello, everybody, and hello, Sonam. Good afternoon, Kaya. Thank you, and hello, Sonam. Thank you for showing an avatar. You guys, there's a lot of black. Good afternoon, Genesis. Thank you. Yeah, it's funny. Different times of day seem. Good afternoon. All right, here we go now. But it's funny. Maybe from now and again, some of you guys may want to experiment with if either video or at least avatars or something just to break it up. There's something about this time of day that seems, or this section that seems to be a lot of black boxes. But okay, but good, but thank you for the chat. So who we say? Good afternoon, Kaya. Thank you. Good afternoon, Genesis. Thank you. Good afternoon, Sonam. Thank you for the avatar. Um, Good afternoon, Matthew. Um, Thank you for being so early, Matthew. I did catch that. Good afternoon, Sydney. Thank you. Good afternoon, Erica. Good afternoon, Gabriella. Good afternoon, Alfred. And thank you for the avatar, even though it does creep me out. But no, but see, but it's better than. Oh, and there's Kaya. Oh, that is like. Oh, she just. All right, fine. That can't. Oh, yeah. Oh, all right. No, that counts either way. I appreciate it. It means a lot. Thank you, Kaya. Like, even if it's. It really does. Thank you. Hello. Good to see you. Oh, why is my. Oh my God. And now I'm being freaky. What is happening with. Okay. Um, Here they come. No, it takes a lot of guts, especially if you're like the only one. It's very noted and appreciated. Oh, all right, fine, fine, that works too. Now, by the way, just very quickly, wow, that's a nice one. I like the background too. And notice, folks, what Kaya just did, even though she did regular video, I'm not trying to, make a big thing, but there's at least two portals that she can now submit for points, right? Even for the 2 minutes that she just did regular video, she can submit to the video portal. Plus, now she's doing the animated avatar. That's a portal. So just be aware. I mean, I'm not, it helps. It helps everything. But again, thank you, Kaya, for that, and thank you, Sonam and Alfred and Yaneli and Brian. Even what Brian's doing counts as something that's just breaking up the monotony. Okay. Anyway, and I help you identify. And thank you, direct chat person. I see the direct chat. Hello, thank you, and good afternoon, Brian. Okay. All right. So I think that's. Did I say Yaneli? I'm sorry. I keep not saying Yaneli. I'm so sorry. And Yaneli, absolutely with the avatar, or maybe I did say it, but and very reliable avatar, and very helpful, uh, consistent. So thank you, Yaneli. If I don't know why I didn't say Yaneli. Did I? Maybe because I didn't see her in the chat. All right, anyway, whatever. Oh, Gabriella. See now I mean, be still my all right. All right, I won't make a big deal. I did. I did. Thank you, Yaneli. All right. Oh, and that's a portal too. What Yaneli just did, just by like acknowledging like that she's in a conversation, right? That's closing a conversational path. Again, I'm not trying to make a big deal out of all this or any one of you individuals, but I also know we're getting to that time of year where it's like harder to show up to class. It's harder to pay attention in class for sure. And the irony of this time of year is because everybody's like gets so worried about grades, it gets harder to do work, if you know what I mean. So I'm also just like as a gentle reminder for people that are still getting used to the grading system or whatever, all of those, and some of you totally take advantage of this, don't get me wrong, but some of you still might be confused or worse. Some of you might think it's too late, which it is not. All of those portals, those game portals that are all technically due like December or something, that's just a way of saying, well, first of all, they're all optional. Invariably, right as we get to finals or something, there's invariably people that sort of haven't really been following anything at all and then see all those portals and suddenly think they have to fill out every single one in one day. And that's not the case. All of this game stuff is extra points that really do help a lot, but it's all optional. So on the one hand, if you see a bunch of portals that are all due, I don't December 6th or near the last day of class, I'm not saying suddenly you have to do all of those. On the other hand, I am saying now, before it's too late, like you have not missed the opportunity, none of you, like the video portal just means any or every time that you show video, just put a screenshot in there and remind me that you showed video, and you get points for this. So like, for example, Gabriella, thank you very much. Like, she can get points, and I know she's done this before. Every single time she's done it, she can get points for that. And there's all kinds of things. It's not too late to be grabbing points wherever you can to help make yourself feel more secure and engaged in the class. Anyway, I hope you understand. But so a lot of them have silly names. A lot of those portals have like silly, gamey kind of names. Just read what they actually mean. Don't let the names fool you. Like if one says speak now or forever hold your chat, read the instructions. It means anytime you use your voice at all, you can just submit for points. All right. Anyway, I don't know why. I'm happy that some of you are taking me. Thank you. All right. So I'll go on. Okay. So what we have to do today is go back to, well, we're going to do more physics, obviously. What I'm going to switch. Oh, there's something in the, oh, there's a lot in the chat. Oh, I did. Okay. 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 First of all, just to remind you where the, what we're doing is this problem, right? You can see on the screen, yes. We were in the middle of it yesterday. We're going to continue. We're going to continue finishing this problem, the what multi-force, the apple problem. But then the goal again is, just so I don't confuse you, the goal is to finish walking through the answer for this problem. But then we're going to add a bunch of features step by step to this problem to make it look more and more like your lab situation, lab 5, okay, which is hard. Lab 5 is a hard, involved Newton's law problem. It's a hard force problem. What I want to emphasize today, what I was trying to emphasize Monday, is there's a procedure, there's a way of solving these hard Newton's law problems that once you understand the procedure, it works no matter how hard the problem is. But you have to take the procedure very seriously. The procedure in summary, the procedure is you draw a system schema. From the system schema, you draw a pure free body diagram. From the pure free body diagram, you draw a component free body diagram. From all the component vectors in your component free body diagram, you then write down F net equals ma. You write down Newton's second law once for each axis of the situation. And the way you know how to expand, the way you know what to write down for F net in the law is you literally just take every single arrow that's in your component diagram and all of the arrows that are along a certain axis in your component diagram all get added together and become the F net of F net equals ma. So so you'll see that. Well, that's what I'm about to do today. But I'm saying that even if a problem looks really intimidating and has all kind of features like friction or like an angle, stuff like that, the procedure is always picture, 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 picture until the picture is so broken down that you have a bunch of arrows going in one axis and a bunch of arrows going in another axis. And then each of those axes you apply F net equals ma. What is F net? F net is the sum of all forces. What are all the forces that you sum up, that you add together? All of the arrows along an axis of your final diagram. So if you really follow these pictures seriously, by the time you get to your component free body diagram, then it pretty much sets up the equation for you. What's the equation? F net equals ma. How many times do you do that equation? Once for each axis of a problem. So like that's the larger procedure. And I'm going to try to show you that now with the Apple situation. And I'm just going to make, good afternoon, direct chat person. Thank you. I'm just going to make the Apple situation more and more like the lab situation is the whole idea today. Okay. But first, let's just like finish where we were yesterday. So the Apple situation I'm talking about is the one right here on the screen. Um, Right, and where we left off yesterday, was part 4 of the Apple thing, where it says to. So I'm going to switch the screen back and it pick up where I left off yesterday, which was part 4. So bear with me, switching the screens. Okay. Okay. So, okay. All right. So this is part 3, the pure free body diagram. This is the pure free body diagram of the apple. We've got the weight of the earth pulling down. Excuse me. We've got the gravitational pull of the earth pulling down on the apple, which we call the weight of the apple. We've got the desk, the table, pushing up on the apple. So that's the diagram as it stands now, just of an apple sitting on a table. It came from the system schema. Couple things to notice about this diagram. One arrow in the diagram, the MG, is in every single diagram, no matter what. Like, that's the first thing you always identify in a system schema is entire Earth, and the first arrow that becomes in every single diagram, certainly including the lab. There's always MG pointing straight down because there's always planet Earth right below our feet, pulling on every object straight down, right? So for example, if you're trying to track this for the lab, in the lab, is there a downward arrow of MG? Yes, there absolutely is. Okay, because there always is, right? Then we've got this upward arrow here called the normal force of the table. What I want to emphasize right now before I go any further, again, the whole goal of what I'm trying to do is build you up so you can feel comfortable with the lab situation. So I'm sort of trying to do a compare and contrast as I go. So this upward force called normal force, like, how does that relate to the lab, or what's going on there? Well, first of all, please remember that normal just means perpendicular. The normal force here in this situation is there because we identified in the system schema, we realized there's a table that has there's a surface of a table that is touching the lower surface of the apple. There are surfaces pressing against each other. Surface of the table is pressing up against the surface of the apple. Whenever there are surfaces pressing against each other, we call that press, that againstness, normal, because normal means perpendicular. And what we're really identifying is, oh, if here's the table and here's the bottom surface of the apple, like if we imagine like they're a little bit of a sandwich and there's like a layer in between there's like a thin plane, Euclidean two-dimensional plane between the two surfaces. They are pushing against that plane. They're pushing perpendicular to that plane, right? So the normal force means the extent to which the table is pushing perpendicularly to the plane of contact between the table and the apple. Oh, that's a long way of saying it's normal because it's perpendicular. It's not normal because it normally always has to be there or be in that direction, or be like, what I'm trying to say right now before I move on is, does every single situation in physics have an MG downward arrow in it? Yes, definitely. Does every single situation in physics have an arrow called normal? No. There's a lot of situations in physics where there's no normal force. For there to be a normal force, there have to be things pressing against each other. Okay, that's number one. Number two, when there is a normal, so not to trick you, is there a normal force in the lab? Yes, there is. Yes, there is, because there's a track and there's a ball on the track. And so the surface of the track is pressing against the surface of the ball. So does the track exert a normal force on the ball in the lab? Yes, it does. But is the normal always pointing equal and opposite to gravity. No, it is not. Okay, again, this is a compare and a contrast. Is there a normal in this diagram? Yes, there is. In this diagram, does the normal seem to be pointing in the opposite direction of gravity? Yes, it does. Does the normal seem to be equal magnitude to gravity? It turns out, yes, it does. We're going to explain that in a minute. But is that a law? Did that have to be the case? Is it the case in your lab? No, it is not. To cut to the chase, in your lab, the normal force in the lab is perpendicular, like always the normal force is perpendicular to the surfaces. So in your lab, the normal force is going off on an angle, because like the track in your lab is like this, let's say. So the normal force from the track is going off at an angle. Does that mean gravity's going off at an angle? No, gravity is always straight down. So again, I'm not trying to confuse anybody. I'm just trying to do a compare and contrast. Just because there's a normal doesn't mean it has to be opposite or equal to gravity. You have to think of the normal just in its, the way you analyze the normal is you apply Newton's second law to whatever axis the normal is in. And that is different for every situation. And some situations don't even have a normal. Okay, I'm saying too much. So what we're going to do now is we're going to analyze how the normal force and everything work in this situation. Whatever rules I say or whatever general principles I say about this situation, the general principles and rules apply to your lab. But for sure, the way it plays out in details is different. Okay, so what am I saying? I'm saying I look at this situation. It looks like I have two forces that are opposite in direction. I mean, they are. And it looks like I have two forces that are equal in magnitude. I mean, I think they are. So what I might think to myself is, oh, is this an example of Newton's third law? I might think, oh, and everybody does think this, honestly. I might think, oh, I guess the downward pull of the earth is an action, and the upward push of the table is like the reaction. I guess this is wrong, what I'm saying, okay? But the homework problem asks in part 2, and also I know I'm being repetitive. I know I said this at the end of last class, but I just want to be super clear about this. The homework asks, part 4, it says, name all the action-reaction pairs, or name all the Newton's third law pairs implied by this diagram. And why it's asking that is it really wants to drive home, this is not a pair. The law did not say that just because the earth is pulling you down, a table must push you up. That can't be the case. That couldn't be a law, because then nothing would ever move. If every time something was pulled down, something else would push it up, nothing would ever move. What the law says, so the homework question. So the question says, what are the Newton's third law pairs? And what I'm saying, as I said Monday, is every single arrow in the diagram is an action of its own action-reaction pair. Every single arrow is one half of its own action-reaction pair. And the reaction we don't see in this diagram. It would be in some other diagram. What do I specifically mean? You can tell me to go back if you want. So that said, sorry, I'm not trying to go too. That said, each arrow is an action in its own action-reaction pair. Its reaction is in some other free body diagram. What do I mean? I mean this. And I know, again, I'm sorry. I know I said this Monday. But I can't emphasize this enough, apparently. I'm saying you look first, but also this is you should stop me if there's questions. Since I'm spending 2 days on this point, I'm willing to spend the time on it. So please ask me questions if I'm confusing you. I look at the MG arrow. What it means is that the earth is pulling down on the apple. That's an action. Therefore, the apple is pulling up on the earth. That is in another picture somewhere that I haven't drawn. That is not what N means. N means the table is pushing up on the earth. That's a totally different force. I'm saying every force is a tug of war. If the earth is pulling me down, then I'm pulling the earth up. Every force, by definition, is a symmetric interaction between two objects. So action is the earth is pulling down on the apple. reaction is apple is pulling up on the earth. That's a force pair. Then, and that would be true even if the apple were in free fall. If there was nothing else going on, if the apple's just like falling to the earth, then that's happening. The earth is pulling it down and it's pulling the earth up. End of story. Now, it also happens that this apple's on a table. So there's this other force, the normal force from the table that's just there because the table happens to be there. The table's pushing up on the apple. Therefore, by the definition of forces, by Newton's third law, since the table is pushing up on the apple, therefore the apple is pushing down on the table. That is the reaction. And where do I see that in the picture? I don't. That would be in a picture or free. Well, where do I see it in the free body diagram? I don't. I would see that in a free body diagram that I might draw of the table, or more particularly, like, do I see that anywhere? Yeah, I see it in the system schema. Remember, in the original system schema, there was a picture of a table and a picture of the apple, and they had lines connecting them. The lines were trying to express this exact idea. And they were lines, not arrows at that point, because they're trying to show it's a mutual interaction. If the table's pushing the apple, then the apple's pushing the table, boom, they are in an interaction. Right, I think you get it. I'll move on. But so that's the answer to the question, question 4, middle Roman number 4 of the homework. Those are the pairs. What's the takeaway? The takeaway is the up and down arrows of your free body diagram in this apple case, they are not a pair. They are two halves of two different pairs. Okay. So the next. Okay, now I have to address. In fact, I'm sort of doing this out of order here, but are those two arrows equal? So again, in your lab, the two arrows would not be opposite direction. The normal would be going off on an angle, and MG would be going straight down in the lab, okay? Now, what about magnitudes? Don't those arrows look like they're the same magnitude here in my case? Oh, yeah, they do. And are they? Yeah, they are. Are they in the lab? No, they're not. Like, so they don't always have to be. How do I know they're of equal magnitude here? How do I even know that? Well, it's not because of Newton's third law. It's because of Newton's second law. Let me do a quick example of how you use Newton's second law, because that's like actually the point of all of this. So let's look at how Newton's second law applies and shows us, and again, stop me if the pages are going too fast or whatever. How does Newton's second law lead me to the conclusion that in this case, the normal up from the table balances the weight downward from the earth? Well, I write down F net equals MA, like in the middle of the page here. I write down the law, and I'm going to write it down once for each axis. Here, there's only one axis, the y-axis. So I write it down. So I'm literally saying the sum of all the forces in the y-axis equals mass times the acceleration in the y-axis. Now I add up all the forces in the y-axis. Here's the key. How do you know what all the forces are to put in the math, in the equation for the y-axis? But because of your picture. The whole purpose of all these pictures is so that this step right here, where I expand the left side of F net equals MA, like that, this is the key step, is writing down all of the forces that add up to make F net. Let me say this again a different way. F net equals MA. F net means sum of all of the forces in a particular axis, taking into account negative signs, right? F net means add up all of the forces in a given axis, take into account negative signs. How do I know what all the forces to write down from a given axis? From the arrows in my FBD. That's the purpose of the FBD. So I look at the arrows here and I say, oh, there's an arrow pointing up called N, called the normal force. So I write that down, N. And I'm going to add to it the other arrow that's pointing down, called MG. I'm literally adding them together. And if there were other arrows, I'd throw them in also to the left side of F net equals MA. I'm literally just itemizing. I'm expanding the left side by itemizing every single arrow that I see in a given axis. It's why it's so important to draw the arrows correctly. But once I've written them, so I'm adding up all of the arrows, but any arrow, but I'm taking into account direction. So I'm saying in my mind, all right, anything that's pointing up, let's say, is called positive. Therefore, anything that's pointing down, let's say, is called negative. So the MG got a negative sign. I'm gonna move on. I know I just sorry. I don't even know why I'm laughing. I just get so anyway. Uh it looks like I'm subtracting forces. What I'm trying to say is I wrote N minus mg. I just want to emphasize it may look like subtraction, but what I'm always doing is adding. F net means add up all the forces. It's just if some of the forces are going in a different direction, they get minus signs. Okay. Okay. So I write down N minus mg equals ma. Right? This is an example of, okay. And then I say to myself, oh, the A in this case, like typically we're using the F's to solve for A, but sometimes on certain axes, you know the A, so you use the A to get the F's to solve for the F's. In this case, I know this apple is not accelerating up and it's not accelerating down. The apple is just sitting there. So I know the acceleration along the y-axis is 0. So I plug in 0 for A, and 0 times anything is 0. So the whole right side of the equation is 0 here. So from that, I can bring the mg to the other side and say, oh, I get it. In this case, n equals mg, like it does. And that like answers the next question in the homework. Like in this case, in other words, I just solved for the normal force and found out that the magnitude of the upward force exerted by the desk is equal to the magnitude of the downward weight of the apple. Again, I figured it out. It might look like it's obvious to people from the picture, but it's not so obvious that it's always the case. I figured it out. I figured out what the magnitude of the normal force is by applying Newton's second law to the axis that the normal force is acting on. I'm saying that loudly because I'm a crazy person, but also because that's a procedure you're going to follow even in the super complicated situations like the lab. Like whenever you need to solve for the normal force, like in the lab, you go to the axis that the normal force is pointing along and you add up all the forces and say that they equal, including minus signs, and you say they equal ma. And that's how you solve for the normal force. In other words, here, here the normal force is mg. In the lab, the normal force is not going to equal mg. I mean, to cut to the chase, just to help you out a little bit, it turns out in the lab, the normal force is going to equal mg times cosine of theta. There. I mean, that's a giveaway. That's a spoiler alert or whatever. But I'll say it again, though. The normal force in the lab does not equal mg. It equals mg cosine theta. Because in the lab, the normal force is not equal and opposite to mg. It's not along the same axis as mg. It's along the same axis as one of the components of mg. I mean, I'll get to that. But again, this is like a compare and contrast day. The procedure that but how do you find that out? Or why would you believe what I just said? Look, and I also know many of you like already sort of just memorized that or like took it on faith from the lab, but there's a reason for it. It's all consistent. The procedure is what I'm doing right now, one step at a time. Okay, I'm getting ahead. So just to put in numbers, to start putting in numbers and making this more concrete, let's just say, for example, as it says here on the board, say, for example, that the mass of this object is 2 kilograms. Okay, just to be clear, just to make this concrete, say, for example, the mass of this apple is 2 kilograms. Okay, what would that mean? Well, that would mean, first of all, that mg then is 20 newtons. Right? Just like mg, the weight of the apple is mass times free fall acceleration. Weight is a force measured in newtons. A newton is 1 newton is 1 kilogram times one. Sorry. Oh my God. No, yes. 1 newton is 1 kilogram times 1 meter per second squared. Right? So just to make this concrete, if the apple had a mass of 2 kilograms, then it would have a weight of 20 newtons. That means the earth is pulling down on the apple with a force of 20 newtons. Well, then in this case, first of all, that would mean the table is pushing up with a force, a normal force of 20 newtons. Like all forces are measured in newtons, whatever the force is called, right? So in this case, if the weight were 20 newtons, the upper normal force would be 20 newtons. Again, that's not true in your lab. But similarly, just so you know also, if you're really seeing what I'm saying about Newton's third law, that also means that the apple is pulling up the earth with a force of 20 newtons. That's how that works. Like the apple is pulling on the earth just as hard as the earth is pulling on it. Does it matter as much? No, because the earth is much heavier. So like the apple is pulling up with 20 newtons, but F net equals ma. In order to accelerate the earth substantially, you would need a much bigger force than 20 newtons because the earth has a much bigger mass than 2 kilograms. But anyway, so okay, so I'm just putting numbers in to start making more concrete. Hold on, sorry, I'm also changing the view on the screen. Pardon me, sorry. Okay. Oh, so did I answer? Wait, I want to make sure. I believe now I've answered all the actual homework questions of that problem. Like, yeah, so I'm just in the homework problem. I'm not, and again, well, anyway, in that homework problem, 3A about the apple, it then asked part 4, it asked for Newton's third law pair implied by each. We just did that. Then it says compute the force that the entire earth exerts on the apple. Yeah, that's what I'm doing here is part 5. And then part 6, it says use Newton's second law to compute the force that the table exerts on the apple. So I did that out of order. I apologize. But the answer to that is 20 newtons. Okay, so that's it for that problem. As far as the homework is concerned. But now, and I'm going to ask, now what I'm going to do, like that was homework 8, problem 3, part A is what that was. Now, instead of moving on to a different homework problem, I think it's much more useful for your understanding and for your grades, honestly, is if I just start expanding this problem now, adding features to make it more and more like your lab situation. Because your lab situation is kind of like the hardest possible version of all of this in a way. So that's what I'm going to do now. Right. So I'm getting confused by my screen shares. Okay, so I'm going to increase so we got an apple on a table, okay? I'm going to start adding elements to this apple, and I'm adding them right now. They're not on a sheet somewhere. They're not in a sheet. I'm just doing this right now. So we're going to increase the complexity of the situation step by step. So the first thing is like, I'm going to say, what if someone were pulling the apple at an angle of 30 degrees relative to the horizontal so that the apple slid horizontally across the smooth table. In other words, this. Okay, so sorry, I don't know. So we got an apple on it. So this is my picture, like my DFP, step 1. We got the apple on the table. But now, and it's still the same app, so it still has the same weight as before. We're still saying, let's say its mass is 2 kilograms, right? But now there's like this rope that or like a fishing rod with a fishing line, and you're like pulling on the apple at an angle. Why at an angle? Just because of leverage, like because it's just easier for you to do that than to like squash yourself onto the table or something. So you're pulling at an angle, but let's assume, and this often happens, like the apple slides along the table horizontally. Like you're not trying to get the apple off the table. You're just trying to move it along, but because of the way you're standing, you pull it at an angle. Okay. So what my question is going to be, now we're dealing with numbers, now we're dealing with problem solving. My question is, can we use and let's just say, I'm just saying, for example, that the angle is 30 degrees and the amount of force that you're pulling with this string is 30 newtons. Whenever people pull with a string, whenever a string pulls on something, the name of that force is called tension. Just like the name of the force of one surface pushing against another is called normal, the name of the force for a string pulling on something is called tension, as in the tension of the string. Okay, so I'm just saying, let's say the tension in this string is 30 newtons. Let's say the angle happens to be 30 degrees. That's the new situation. We're gonna try to do 2 things. Actually, our ultimate goal is to compute the horizontal acceleration of the apple, but I want to make something clear. Okay, so I'm adding here, what I'm adding is, first of all, another force to show how even every element that you add, if you really follow the whole procedure, the procedure can accommodate all the elements. But also the specific element that I'm adding here to make this look more and more like your lab is an angle. Like, how do we deal with angles like that? That's really my issue right now. Well, I've got bigger issues than that, as you can see, but so our goal is to solve for the acceleration of the apple horizontally along the table. That's the goal, but I'm actually putting in this reminder here to the side in white. I'm saying, you know what? Along the way, while we're solving for that goal, let's also be mindful and see if we can solve for the magnitude of the normal force in this case. Because warning, like, I don't think the normal force is going to be the same as it was before. And warning, like, it's not the same in the lab. So, like, we're going to use this as a checkpoint to, like, how do you deal with the normal force in a situation like this, even when there's angles and stuff, okay? So the goal is to solve for the acceleration. Okay, sorry. Hold on 1 second. There's something in the chat, just sorry. Or is the chat already, okay. Hold on. A direct chat person, hang on a second. Okay. But thank you, direct chat person. I get it. Yeah. Oh, thank you. Okay, cool. And to the rest of you, I'm about to move on. I know I'm spazzy, but are we just give me an electronic hand? Because this is now going to, I think, start becoming more directly helpful to your lab situation. So give me an electronic hand if you like get basically what I'm doing right now. Like, I'm about to solve. Thank you. Okay, great. Thank you. You guys are so good. See, you don't show video, but you do show video. All right, I love it. And that's Portal 2. For those of you who still don't understand how the grades work, like the fact that you even just raised a hand, any one of you, there's at least one portal for that where you can get points just for the fact that you just showed me that you're still alive and with me. So thank you. I appreciate it. Okay, so here we go. I'm going to solve. And the procedure that I'm doing to solve now is the procedure that you would do in the lab or any exam problem or something. The procedure is, first of all, I draw a system schema. And the system schema is the same as before. It's just I've added a new element now, right? Like the Earth is still there. It's always there. So I draw this. I'm sorry, let me back up. I have a dotted circle for the mass, the mass of my concern, right? Then I've got solid circle for the Earth because it's always there, and the Earth is always interacting with your mass, whatever your mass is. So there's always a line connecting the Earth to your mass. It's always one line, even though the Earth isn't touching. Somehow, always the Earth can pull on us without touching. So we just put it in there right away. Always, it's still there, right? Then we've got this table that's still there in the problem. So the table is sorry. So once you draw the Earth, then you draw anything and everything else that's touching your object. So the table is touching my object. And literally, it's about Earth plus touches. It's that simple. So the table is still touching my object. So I draw a table, right? And I don't care where I'm drawing these objects because in the system schema, it's a schema. It doesn't matter about direction. We're just trying to identify what's going on. So the table is there. It's a solid circle. And then the technicality, the subtlety is that the table is a surface pushing against the surface of the apple. So technically, or to be careful, whenever we have a surface pushing against another surface, we always draw two lines just in case, because one of those lines means this business, right? What we ultimately call the normal. But then we're drawing a second line always just in case the surfaces are rough. If the surfaces are rough, they're also going to have this effect on each other. So, right? In other words, this is the other exception to the one touch, one line rule. When surfaces press, if in case they're rough, They could be, by pressing, they actually do two things. They press, we call that normal, and they rub, we call that friction. So we always draw two lines to acknowledge that possibility, right, in the system schema. Then, and all of that was already there, like just in the original Apple problem. But now I've added this string. I've added this string that happens to be pulling on an angle. I don't care about the angle yet in the system schema. I just know there's another object touching my mass. That object is the string. So I put string in the system schema. You see what I'm, right? And the string is a good example of literally the straightforward one touch, one line rule. The string is an object that is touching my apple. Specifically, it's pulling it. So the string is not a surface pressing. It's a string pulling. So it pulls in one simple way, the simple direction of the string. So it gets one line. Strings, or what we ultimately call the tension force, always get one line in the system schema, which will be one arrow in the free body diagram. So anyway, okay. So I'm just saying my system schema now is just like yesterday, but I've added a new element, which is the string. Sidebar, if you were doing your lab, how does this translate to your lab? Well, in the lab, there's no string. The reason I'm adding a string now is to show you how to deal with angles, okay? In the lab, there's no string. So that there would not be a string in your lab system schema. In fact, your system schema would look like this one without the string. Would there be two lines between the table and your mass in your lab? Oh, absolutely there would be. And both of them would be very relevant because ultimately your lab is all about friction, which is ultimately what I have to explain today, right? Okay. So anyway, that's a system schema for this. Now, I turn it into a free body diagram. Always. The way I turn it into in fact, a pure free body diagram, the way I turn a system schema into a pure free body diagram is that every single line that's in the system schema becomes an arrow in the free body diagram. I'm now that I used the objects to identify the lines, now I'm going to use the lines to identify arrows. And I no longer care about the actual objects that's creating these lines. I now start using the proper names for the forces of the arrows themselves, right? So basically, I just count the lines in my system schema, and each line becomes an arrow with one like sort of subtlety, which is that, I mean, in other words, there's 4 lines in my system schema. So in principle, there should be 4 arrows in my FBD, but note this yellow note. The thing is, at this stage, still with this apple, still when I read the problem or I hear everything Yaverbaum's yelling about today, still with this apple, there doesn't seem to be any acknowledgement of any roughness. No one has yet mentioned that the apple is rough or the table is rough or anything like that. So this idea of sliding, this friction idea, doesn't seem to be acting as relevant in the problem. So that second line in the system schema that I always put in to be careful, to alert myself, I think about it, I'm like, all right, that second line is supposed to be about friction. But is friction really like doing anything in this problem? I.e., has anybody told me any facts about roughness of material? The answer is no, they have not. So I drop that second line. Okay, and again, let me tell you, I'm talking around and around about this whole friction point. I think friction is the most subtle and challenging aspect of all of this stuff. And it's what I'm trying to get to here. But I'm trying to go step by step and break everything down. So I want to acknowledge in advance, like the hardest issue of the lab in a way is the issue in the lab is the friction. I'm getting to the friction. But the first thing you have to realize about friction is that someone's here. Hold on, sorry. The first thing you have to realize about friction, the one thing I'm emphasizing so far is friction is this effect that comes into play whenever this effect happens between rough surfaces. So for there to actually be friction, there have to be 2 requirements met. There has to be this, which we call normal force, and there has to be roughness, which we ultimately call the coefficient of friction. Okay? So that's why we're paying so much attention to when surfaces press against each other. Always be very careful when surfaces are pressing against each other. Acknowledge in your mind that this could lead to that if and only if the surfaces are actually rough. Because if they're rough, that means if you looked at them microscopically, they're locking in with each other, right? If they're actually rough, it means that when they press against each other, they're like teeth of a comb, and they're like harder to go like that. I mean, if it's a hockey puck on an air hockey table, or if it's a smoothly polished apple on on a polished table, then it doesn't matter. Like, because then even going like this, they're so smooth, it doesn't. Anyway, all right. So my free body diagram has 3 arrows in it because one of the lines that was meant to be friction, I was like, yeah, I don't think I actually need to worry about that today. So I don't. So I have these 3 arrows in my free body diagram. I'm looking at the time. Okay. So that's my pure free body diagram. Again, notice it's just like the diagram from yesterday, but now there's a third force added, and the third force is at an angle. How does that compare to the one in your lab? It's very similar. Your lab would have 3 forces in it. Sorry. Yes. Yeah, well, it's similar, but I'm just going to keep going. That's the diagram of the situation right now. Now, what do I do with that? Who cares? Like, what's the point of that? The point is I'm trying to solve for acceleration. And also I'm trying to solve for the normal force. I'm trying to do math now and get numbers. So I'm going to do the math by writing F net equals MA on each axis, one at a time. The problem is I don't have things happening on 2 clear axes in this diagram. I have something happening on like a y-axis, but then I have this cockamamie thing that's going like this, sort of on both axes at the same time. So the next step that I have to do, and that you definitely do in the lab, the next step that I have to do is create a third diagram. I have to make a component free body diagram for which all arrows lie on coordinate axes. Like, I want to make a diagram where every single arrow I see is either on an x-axis or on a y-axis. So how do I do that? Okay, so we must now make a component free body diagram from our pure free body. And I see my handwriting is, please stop me if you can't read the handwriting. Like, that would be a legit, that's also points. It's called please go back. But yeah, because I can't even read my own handwriting. I don't know how you possibly can, but I know Gabriella can. Okay, no, see, what's the point of that? Why did I do that? As a compliment, that's why. Okay, well, we must now make a component free body diagram from our pure free body diagram. We must choose a coordinate system. Okay, this is subtle now. We're going to choose a coordinate. We're going to say, like, okay, this is my x-axis and this is my y-axis. And now I'm going to take, like, the idea is we're going to say from here on in, this is my x-axis, and anything perpendicular to it is my y-axis. And any arrow that I see that is not lying along one of those axes, I'm going to break up into components that lie along those axes, like you did with displacement vectors and velocity vectors, in the earlier material of the course. Like, that's why we were doing that. So the first thing is I have to choose a coordinate system. I have to choose. What do I mean by the x-axis? What do I mean by, well, you might think it's obvious. You might be like, well, duh, yeah, I mean, like, x is always like this and y is like, well, it's not. I mean, it could be sometimes, but it doesn't have to be. The whole point of Galileo is laws of physics work in any coordinate system. The laws of physics should work whether I'm looking at the world like this or looking at the world like this. The laws of physics should still work. Now, I can look at the world any way I want. I mean, as long as I'm not accelerated. I can look at the world through any kind of reference frame or coordinate system that I want, as long as it is not accelerated, right? So you might say, well, then so just look at it normally. Like, don't be a jerk. I mean, just look at the world like that. Well, it turns out that what I'm trying to do is look at the world that will reduce the amount of hard math. I want to look at the world in a way that's as convenient as possible, that makes it as easy as possible to solve the problem. It turns out that the easiest way to solve F net equals MA, since you have to solve it one axis at a time, it's easiest if you make sure that what you're calling your x-axis actually lines up with the direction of expected acceleration. In other words, in this case, I'm expecting that the apple is going to accelerate along the table horizontally. So yes, in this case, I'm going to say, oh, if that's where the action is, if the apple is going to accelerate fully horizontally like that, and it's not going to accelerate at all like that, and it's not, right? It's just going to, we expect that we're pulling it along the table like that, just because that's what the problem said. Then it's easiest to say, it's most strategic to say, okay, this is the x-axis, and this is the y-axis, because when I go to apply F net equals MA to each axis, then along this one, it's going to be 0. So that's going to give me a lot of fast information. Like I already know that one of the numbers is 0, so it's very easy to solve. And along this one, the acceleration that I'm looking for, I'll know that any acceleration I find is fully the answer I'm looking for. In other words, I won't have to deal with sines and cosines for acceleration. So, okay, I'm over talking this as usual. I'm saying in this case, since the apple is expected to accelerate like that horizontally, I'm going to line up. I'm going to look at the world the way you would expect me to. I'm going to look at the world and say, that's my x-axis and that's my y. Why I'm saying all this is, if you really are, okay, it seems like I'm over talking, I am over, but instead of just writing down the details of what I'm about to do, if you're actually following the larger principle that I'm saying, if you actually hear me, that I'm saying always choose an x-axis so that it lines up with acceleration, choose plus x so that it lines up with plus a. If you really follow, that's what you do in the lab. That's what you do in the lab. And in the lab, therefore, you do tilt your head. And this is the part that confuses a lot of people. Okay, so there's a slight sidebar here. Again, if you write down anything right now that I'm saying that isn't written here, screenshot it and submit it for points. Like if you can follow what I'm saying right now and make a note of it, even though I didn't write it right here, like I would be delighted to reward you or to incentivize you for that. Because what I'm saying is this. We line up our x-axis to we line it up with expected acceleration so that we can solve F net equals MA as easily as possible, one axis at a time. Therefore, in the lab, when the object is expected to accelerate along a slant, along an inclined plane, we tilt our head and we say, okay, the x-axis is along the inclined plane. It doesn't change the pure free body diagram. The pure free body diagram is what it is. It's pure. But when you start breaking things up from the pure free body diagram into a component diagram, the thing you have to do first always in physics is choose what is my x-axis. And in the lab, you're going to choose that the x-axis is like that. Therefore, in the lab, you'll notice that the normal force is totally along the y-axis. It's fine. And friction in the lab is totally along the x-axis. It's fine. It's half the reason you're tilting your head like this. But it's gravity, mg, in the lab where you go, wait, like gravity is just pointing straight down. But now suddenly I just tilted my head to watch everything. So even though gravity is pointing straight down, that is no longer pointing along an axis. The y-axis is not straight up and down when you analyze the lab situation. Why? Because the acceleration is not straight up and down. So in the lab, you end up having to, so what I'm about to do here, I'll bring it back. So what I'm about to do here is say, okay, here's the slightly easier situation from which we build the lab. Here, the thing is accelerating horizontally. I look at it head on, and I'm like, fine, here's my x-axis, here's my y-axis, as everybody would have expected. And so I say, therefore, in this situation, it's the tension. I say gravity is perfectly fine. Gravity is just pulling down along the y-axis. No issue with gravity here. And no issue with the normal force. It's just pointing up. But it's the tension in the string that's at a cockamamie angle. So here in this situation, I zoom in on the string, on the tension in the string, like as you see this diagram. I zoom in and I say, oh, that arrow is not x nor y. I'm going to break it up and say, I'm going to say, like we used to with displacements and velocities, I'm going to say, oh, I mean, this is kind of like any any two-dimensional problem is really two one-dimensional problems occurring simultaneously yet independently, right? So I say, oh, even though I could believe that the string is pulling up and over at an angle of 30 degrees, really, that's equivalent to a string somewhat pulling up while at the same time it somewhat pulls over. How much somewhat? In other words, some of its 30 newtons are going to this kind of activity, and some is going to that kind of activity. How much each depends on how big the angle is. That's what sines and cosines are about. SOHCAHTOA, right? The opposite component is like the sine of the angle is the opposite component divided by the hypotenuse, and the cosine of the angle is the adjacent divided by the hypotenuse. So the string is pulling up with some percentage of 30 newtons. What percentage? The sine of 30 degrees percentage, 50%. And it's pulling over with some percentage of 30 newtons. What percentage? The cosine of 30 degrees, 87%. 0.8, you understand what I'm saying? So I zoom in, I'm looking at the clock. Okay. I zoom in and I say, it is true that the tension is pulling at an angle, but I can't deal with that in any F net equals MA equation. I've got to get the job that the tension's doing in the y-axis, and independently from that, the job that the tension's doing in the x-axis. So I zoom in on the tension, I break it up into those two components, T sine and T cosine, right? And I use SOHCAHTOA to figure out which one is which. And that, though, now from in the next moment when I turn the page, it's those two components that I'm going to put into my diagram. Like I'm trying to get rid of diagonal lines in effect, or I'm trying to get rid of lines that are not lined up with axes. So I take out the tension from my diagram and I put in the sine component of tension and the cosine component of tension. You're doing the same thing in the lab, only again, warning, in the lab, it's gravity that you're breaking up. And please note, I'm going to say it one more time, I'm going to move on. Here we don't break up gravity. There you do. That can be confusing to people. It's one of the confusing aspects of the lab. Is like, why are we breaking up gravity, or how are we breaking up gravity to mg sine and mg cosine? What I'm trying to do right here is show you what the larger idea is, that actually the larger rule that you're following in both cases. It's confusing. It's hard. I'm sympathetic, but it's not a contradiction. What you want, and if you just memorize things, you won't see it. What you want to see is the rule is we're breaking up forces into components that lie along axes. We choose the axes to line up with acceleration, and then we break up. Breaking up is hard to do. I'm sorry. But okay, so here in this case, my component diagram therefore looks like this. Again, please note, like I had a pure free body diagram a moment ago that had a total of 3 forces in it, right? Now I have a diagram that has 4 forces in it because I just swapped out the tension and substituted in instead the upward component of tension and the horizontal component of tension. Quick pro tip or quick sidebar thing. If this is in an exam problem, which it always is, a common mistake that people make, even when they sort of follow everything I'm saying, is they'll somehow put the sine and the cosine in their diagram and also put in the tension. And in the lab, people often do that. They put in mg and mg sine and cosine. No, please. If you're following what I'm saying, the idea is that sine and cosine together make the tension. If you put also the tension diagonal line in here, you've defeated the whole, first of all, you've defeated the purpose. And then second of all, you've double counted tension. So, okay, so this is my new diagram. This is the component diagram. I can tell that it's a proper component diagram because everything is parallel and perpendicular to everything else. Like there's no diagonal, right? And in the lab, the whole thing is different. But again, you have arrows going like this, and you have arrows going like this, and that's it in your final component diagram. Okay, so now what do I do with this? I solve one axis at a time. What do I mean by solve? I apply F net equals MA, Newton's second law, to one axis at a time. So, and pro tip, I always go, and this is going to be weird. Oh my God, if you write that, I need to make a new portal for like specific pro tips or whatever. Maybe I will. If you write this down and screenshot it, not only will I give you points, I would like worship your soul for a long time. That's weird. What is it that I want you to write down? I want you to write down. Oh yeah. Always solve for the axis. Always first solve for the axis that you care less about. The reason I want you to write that down is it's super important, but it's also like super counterintuitive. Like, who would think that? What I mean by that is this problem is asking me to solve for the acceleration along the x-axis. In fact, most problems do, including the lab. It's asking, my ultimate goal is to get the acceleration along the table. So my pro tip is I'm going to do F net equals MA one axis at a time, but I'm going to leave the important axis for last. That is a strategy. That's not a law, but it's a really helpful, important strategy. So, and you'll see why, I think. So I'm going to go to the y-axis first. I go to the y-axis and I say, okay, the sum of all, so I write down F, okay, so it's always about F net equals MA now. All the problem solving comes from F net equals MA, this Newton's second law. The first and the third are getting the concept nailed so we know what we mean by forces and whatever, and how to draw the diagrams and all that. But the math all comes from the second law. So I write down sum of all the forces equals MA. That's a vector equation. It reminds me, by being a vector equation, it means it is true simultaneously yet independently along each axis, like separately. So I go to the y-axis. Sum of all of the y forces equals mass times acceleration in the y direction. Like I put the subscripts, right? So now here's the key move. Here's the key move that if you have been staying awake with me for all of this, this next move will seem obvious to you, hopefully. But it is the key move. And it's only obvious if you follow all the stuff coming before it. We now expand the left side of F net equals MA. The whole key to doing all the math is knowing what to write for the left side of F net equals MA. And the way we, suddenly, look in the middle of the page, suddenly the left side got exploded. And it looks pretty fancy and complicated. And I can't find my stylus. And I'm yelling at myself. No, here, I'm saying this is like the key step right here. And once you get that step, then we're just going to plug in numbers and it's all going to work algebraically or whatever. But that's the setup that nobody knows how to do unless they do all this stuff before it. But if you do all this stuff before it, then where did I get that from? I literally just read it off my picture. I look at I follow the procedure that I did 10 minutes ago when the picture was easier. And again, this is what you're doing in the lab. I look at the y-axis and I see there's three forces in the y-axis. There's a normal force, there's a t sine theta force, or force component, whatever, and there's the mg force. So I'm literally just going to write those all down. I'm adding those all up and making that F net in the y-axis. Only the mg happens to be going down while the other two are going up. So mg, I'm giving a negative sign. Okay. So I literally have n, I have positive n and positive n t sine theta and negative mg all added together make ma in the y-axis. That's my statement for the y-axis. Now in the y-axis, why do I always start with it? Because if you've done this correctly, you've chosen an x-axis which lines up entirely with the acceleration. Therefore, the y-axis, whatever it is, will necessarily have no acceleration. So we always have this extra information about the y-axis, which is that a sub y will equal 0. Again, this is true in the lab. In the lab, the statement wouldn't be this. I'll even just say it if it helps. In the lab, the statement is something like n minus mg cosine theta equals ma sub y. I'll say that one more time for people who are still with me. In the lab, the y-axis would be n minus mg cosine theta equals ma sub y. So it's a different statement, but it came from the picture that you draw in the lab. And the picture is only different because you tilted the picture is different partly because you tilted your head to look at that picture. Blah, blah, blah. So, but either way, so in the lab, the y-axis is like this. But if you write down all the forces in that y-axis, you'll write down n and minus mg cosine theta, and they equal ma sub y. And they're just like here, a sub y equals 0. because the apple is not flying off the table or crashing into the table. And in the lab, the marble is not flying off the track or whatever. So I can say that a sub y equals 0. Therefore, the whole right side equals 0. Therefore, the normal now equals mg minus t sine theta. Notice here in this case, n is suddenly not mg anymore. It's mg minus t sine theta. What does that mean in English? It means the table doesn't fully support the apple anymore. It's getting help from the string that's pulling up on the apple somewhat, right? So the table only has to support the weight minus whatever help it's already getting from the string. So the normal force in this case, if I'm solving for it, is 20 newtons minus the 15 newtons, i.e. 5 newtons. So I'm just writing that down. I know I have 9 minutes left. I'm just writing down just because I asked myself before, like, what is the normal force here? It's no longer mg. It's this. It's 5 newtons, and I'm just making a note of it. Now, am I going to need, and I'm going to move on to the x-axis now. That's the information that you usually get from the y-axis is the normal force. Why do you care about the normal force? Well, maybe in this case, you don't care that much. I'm just making a point about it. But in the lab and in general realistic situations, the reason you care about the normal force is you ultimately need it to solve for the friction on the other axis. So now we turn to the other axis. We go to the x-axis. And the other axis, in this case, all there is the horizontal component of the string, t cosine theta. So t cosine theta equals ma sub x. So I'm solving, so I was asked to solve for the a in the horizontal axis. So a equals t cosine theta divided by m. So now I plug in all the numbers and I get a mistake. Oh, no, yeah, and I get that the acceleration is along the x-axis is approximately 12.9 meters per second squared. And that's the answer that I'm looking for. Okay, that's it. So I did the y-axis. So notice the procedure again. You're going one axis at a time. And you're getting your axis information from the component diagram. You get the components from your pure diagram. You get the pure from the system schema. This is the answer. Now we've got 8 minutes. The real issue is now, okay, so the real issue, the next element that's really the challenge in the lab is how does friction work with all of this? So what I'm going to do here is add the layer of friction now. Like what if there were friction to this exact same situation? Like, how does friction affect everything? Well, what that really means is, what if the surfaces were rough? That would be the difference. Like, what if I'm doing this exact same thing, pulling it, trying to get the apple to go horizontally, but now let's say the surfaces are rough. Can I resolve the problem and get a new number based on that roughness? Yes. How? So what that means, if I'm going to say the surfaces are rough now, the way you know surfaces are rough is someone gives you what's called a coefficient of roughness. If they give you a number that represents how rough the surface is. Now, let me be a little bit more technical now. As long as things are there, and that number is called a coefficient, and it's designated with a lower Greek letter mu, okay? But honestly, to be honest, so I'm going to say for this example, there's a mu sub k of 0.1. So that's the extra information. Say the tables are rough. How rough? 0.1 rough. What does that mean? Here's what it means. But so our goal is in 6 minutes to resolve the whole problem with that roughness coefficient. So what does a coefficient mean? Well, remember, I've been saying that friction is a phenomenon that comes out from 2 factors, this factor and roughness. Well, it turns out the relationship between the 2 factors is as simple as can be. The amount, if you express roughness as a pure number between 0 and 1, like a fraction, a decimal, roughness is it's a ratio. It's how much of this we get. How many newtons of sliding resistance we get for every newton of pressure. So mu is a pure ratio of this number of newtons per this number of newtons. So it's newtons per newtons. It's just a number, with no units, in other words. And it usually ranges from 0. If the surfaces are perfectly smooth, then mu would be 0. And if they're as rough or as grippy as can be, like rubber, it would be like 1 or 0.999999. And glass would be somewhere in between, like 0.4, etc. So from here on in, every surface, if it's rough at all, you'd be given, if a surface is rough, it would have a coefficient that would describe it. But a technicality that I have to express is that actually there's two different cases of friction. There could be friction when things are already rubbing along each other, already sliding along each other, and when they're already in motion, and we call that kinetic friction. But there can also be friction just to hold things together, like why things just don't slip spontaneously, or like my coffee cup on the table. If I just push it slightly, it doesn't move. I have to push it sort of hard to get the coffee cup to slide. So there's already a friction holding things together. It works the same way, same math, basically, but there's two different coefficients. One is a coefficient for the sliding case. We call that kinetic friction, kinetic coefficient. And then there's a different coefficient for the static case, when things are just holding together. Same idea, but just a technicality. Two different cases, two different coefficients. Now, the coefficient that I'm concerned with, and it's always one or the other. You're not ever doing both at the same time. You're either moving or you're not moving. So the case that we're concerned with here, with the 4 minutes left with this homework problem and with your lab, we're concerned in the case where the object is actually sliding over the other object. So we're concerned with mu k. So I'm saying in the end of the day, the force that's exerted by friction is the coefficient of friction times the normal force. Let me say that the coefficient is just a number that represents roughness. It's not a force. It's a number that you multiply the normal force by to get the friction force. So how would this work here in this case? We're going to add friction in as another, we're basically finally going to acknowledge that second line that's in our system schema. We're acknowledging, okay, that's actually a force acting on the object. If the object was trying to move to the right, or is moving to the right, the apple here is moving to the right, then friction is slowing it down. Friction is sliding along that same axis, but to the left. So I add it to, and I'm doing this fast because we only have 3 minutes. So I just went straight to my component diagram, and I'm adding friction to my component diagram. Now my component diagram is starting to look kind of complicated. And again, looking kind of as packed as your lab component diagram. But it's just that many more pieces to be handled by F net equals MA, one axis at a time. So I have friction on the x-axis now. What do? Same procedure. I go to the y-axis first. I solve the y-axis just like before. Now, nothing has changed on the y-axis. It's all exactly the same as before. But why did I have to solve? Why do I have to look at it all? Now, it's really important to realize why I go to the y-axis first. Again, just like that, because the y-axis gives me the normal force of 5 newtons. So now when I go to the x-axis, I could say we got t cosine theta to the right. We've got friction to the left. Friction, kinetic friction in this case. So friction is mu times the normal. And the normal force you don't memorize, you get it from the y-axis, as I just did here. So now I can plug in the number. And again, this is just what you do in the lab. Only in the lab, the normal force will equal mg cosine theta because of the way you're breaking up mg in the lab. But it's the same procedure. So I do, and there's no tension in the lab, but whatever. So I just plug in the numbers. 25 minus so t cosine theta minus mu times the normal. The normal I got from the y-axis, so I plug in all the normal, the numbers, and now I get, and I divide by mass, so I get that now the acceleration is a little bit smaller than it was when there was no friction, as you would expect, because now friction's slowing it down. The acceleration was 12.9 meters per second squared. Now with friction acting to the left, it's 12.3 meters per second squared. And that's how you solve these problems. So thank you for being so attentive, and thank you for those of you, well, thank you for being so attentive. You just keep catching up and I'll catch up with you. And I'm hanging out for a minute or two if there's any questions, but I'm turning off the recording, and have a nice rest of the week.